Okay. So there's two ways to do it. You could make it when you're drawing a molecule, okay? Say, for example, you have something like this. You yourself figure out which atom has a formal charge of minus, and you can know which atom it is. Or you can calculate it. Okay? Say, for example, you have one of these ugly problems in the book. Ugly because they don't tell you where that formal charge is. They're just like, yep, it has a charge of minus. And they say, what is the formal charge of, you know, the chlorine there or the iodine there? Okay? And you can calculate it. Now let me show you an easy way to calculate formal charges. The equation in the book is very difficult to use, and it's complicated and it's tricky and you'll make mistakes. Let's say you want to calculate the formal charge of this carbon in this molecule and this oxygen in this molecule. Okay? Now, if you have a drawing, what you want to do is add your dots on top of the line so you could actually picture them. Okay? And my formula looks like this. Formal charge is equal to the number of electrons an atom wants minus the number of electrons the atom owns. Okay? Now, the number of electrons that an atom wants is the group number, okay? That's the group number. It's not 8. Okay, it's the group number of the element. All right, so keep that in mind. And the number of electrons that something owns is going to be all the unshared, but half of the shared. And that kind of makes sense because, you know, I mean, if you're sharing something, you technically only own half of it. So let me show you how to do it with carbon. So carbon, the formal charge for carbon is going to be equal to the number of electrons carbon normally wants. Carbon is going to be neutral when it has 4 electrons. So that's how many it wants to be neutral. It's the group number. Now, how many electrons does carbon own? We count half the bonds. So I use boxes rather than circles for this math. How many electrons are in that box? 4. So the formal charge of carbon is equal to 0. How about the formal charge of oxygen? Oxygen wants 6. It's in group 6 of the periodic table. To be neutral, it would want 6 electrons. Okay? How many electrons does the oxygen own? Count half the bonds and all of the dots on this atom. How many total electrons are in this box? 2, 4, 6, 7. 7. So 6 minus 7 is minus 1. So therefore, I can go in now and write minus on that oxygen atom. Okay? So the formal charge of carbon is 0. The formal charge of nitrogen is 1. Okay? Let's do another one using my method. So again, we're given this molecule here. Okay. Step 1, I suggest putting dots on top of each of these lines so that you could count things. Okay. So the formal charge for carbon is going to be equal to how many, the group number for carbon minus how many electrons it owns. So we count half the bonds and all the dots. So it's going to be -1. Oxygen, normally it's in group 6. How many does it own? 5. Okay, so carbon has a formal charge of -1. Oxygen has a formal charge of +1. Okay, let's do another one. Okay, so we're going to call this A, B, C, and D. Okay, so atom A is a chlorine atom. It's in group 7. Okay, and we count the number of dots on that chlorine and half the bonds. If you can't see the electrons in the bond, feel free to add 2 electrons on that line. Okay, inside the box there we have 7. So 7 minus 7 is 0. How about chlorine labeled B? Chlorine also wants 7, has 7, so it also has a charge of 0. How about chlorine labeled C? Chlorine wants 7 because it's in group 7 and it owns 7, so it's going to formally have a charge of 0. How about the bromine in the middle? This is bromine. Bromine also is in group 7 of the periodic table. So let's go ahead and carefully identify half the shared and all the dots left over on it. 1, 2, 3, 4, 5, 6, 7, 7. I was for sure thinking something would be plus or minus, weren't you? Okay. So that's basically where you're at, okay, in terms of looking at formal charge. And we'll stop the lecture there. I think we've covered enough of Lewis structures. All right, this is a lecture. We're continuing chapter 7. We've already talked about Lewis structures. Well, we've already talked about ionic bonding, covalent bonding, and we've also talked about Lewis structures. And now we want to talk a little bit more about formal charge. Well, my bad. We've already talked about formal charge. That was in a different video clip that I've merged in with this one. So you know how to make it and you know how to calculate it. So we're good for that. Now, what I want to talk a little bit more about here is resonance. Now, this oftentimes happens when you have molecules with charge. Okay? So resonance structures. Okay? These are different Lewis structures, so sometimes the positions of electrons could have different arrangements in a molecule, and 2 possible answers are correct. Okay, so resonance structures are two or more Lewis structures. Okay, but the real molecule is a resonance hybrid. Okay, this term resonance, you might have noticed what that means sometimes with sound or light or something like that. When 2 musical notes are played, sometimes they combine to give a new sound, and they don't always average. Sometimes they build and mix in different ways. All right, so electrons, since they're waves, can mix in that way as well. So that's why we use that term resonance. If you don't like the word hybrid, use the word average in your mind, but it doesn't mean 50-50, all right? Now let's talk about a structure. Usually I introduce this to the class by asking them, okay class, welcome back. Let's all draw a Lewis structure for sulfate. And I hand them out little note cards. And some people end up, okay, so first of all, I'm not going to go through the dot-to-dot procedure for any of these Lewis structures today. I'm just going to slap up the answers here, okay? So be familiar how to do the dot-to-dot. I'm not using the dot-to-dot procedure to write the answer here. I'm just getting it up here on the screen really quick, all right? So some students' note cards would look like this. Some students' note cards would look like this. Okay, and some students' note cards would look like this. Okay. So all the Lewis structures that you could draw for sulfate, that's the name of this polyatomic ion, should have 2 double bonds to 2 different oxygens, 2 single bonds to 2 different oxygens, and the formal charge of minus would be on that singly bonded oxygen. Now, which answer is correct? We normally have a great discussion in the class about this. Are these the same thing? Can we just flip the, can we just rotate the molecule in some way, or are these different? Are these different structures? Do they have different properties? And we say that, well, sulfate can be an average of all of these in some way, and the real molecule is going to have only 1 sulfur-oxygen bond length, okay? So this is where we write some data on the board. I say a sulfur-oxygen single bond, might be 2.5 angstroms, and angstrom is 10 to the minus 10th meters, and a sulfur doubly bonded oxygen might be shorter at 2.3 angstroms, okay? So do we find a molecule with 2 short bonds and 2 long bonds in it, okay? So, each of these molecules should have 2 short and 2 long, and what we find is not that at all. We find kind of like a molecule that has bonds that are halfway in between the 2 extremes, okay? So we find not a minus charge on any one oxygen. We see a delta minus on all the oxygens, and we see a bond length that's 2.4, an average bond length, okay? And students ask, how is this possible? This doesn't make sense at all. And so this is where I would pull out a fork and a spoon. I would say, here's a spoon. Let's say we could draw a structure like that. And then here's a fork, right? And I said, these are from like KFC or something. They're just plastic utensils. And I said, if we could draw a structure like that, and these 2 were individual structures, but the real structure, what would it look like? Well, that would look like a spork, all right? And I hold up a spork, and then it kind of clicks for students to see that, oh, a spork has a curve-like feature like the spoon, but it also has tines like the fork, and the tines are halfway in between the really long tines of a fork and the 0 tine length of the spoon. So the real molecule can't be seen in a spoon or a fork. It's something that you have to imagine in your mind, okay? We can draw individual structures for the sulfate, but those are a lie. They're just any one seating arrangement for the electrons. The real molecule is an average, and we cannot draw a Lewis structure for the average molecule. It's going to look really weird like this structure down here, all right? So this is where the Lewis structures model fails, but it's used to draw individual resonant structures, okay? So let's talk about the acetate ion. The acetate ion is going to look like this, okay? And again, I'm not following the dot-to-dot procedure here. I just want to jump in and show you really quickly. Okay. Now, Lewis structures differ by the position of a double bond and a single bond. Okay. So first off, you want to keep the skeleton exactly the same. Okay. You want to keep the skeleton, keep the atoms fixed. All right. You just want to draw the electrons differently. Okay. So if we were to draw a resonance structure for the acetate, we would want to draw all the single bonds in exactly the same position. Okay. So try to draw these H's, exactly, copy exactly what you have. So this is what we call single bonds. So we're drawing all the single bonds. Okay. And then what's going to happen is that very simply, the position of the double bond, I'll highlight it in magenta here, is going to be at a different position, okay, over there rather than up. And the negative charge then is going to be in a different position as well. Okay, so here's our negative. The negative is now going to be over here. Okay, let's complete this Lewis structure by completing the octet for the oxygen, and we've got an additional resonance structure. The use of these special arrows denote equivalency, or well, not really equivalency, but it indicates that these two molecules are really different representations. Okay, so this is a lie, this is a lie. The real molecule is somewhere in between. Okay, and that's why we use these special arrows. So that's the acetate ion. We've talked about sulfate. Sulfate has a lot of different resonance structures available to it. All right. Okay. Another molecule, so you should be able to draw these. Now, we're not rotating this, I'm sorry, what just happened? We're not rotating this molecule around or anything like that. We're recopying the positions of the atoms and then just repositioning electrons. I mean, electrons are moving around near the speed of light. They don't really have like a seating chart where they're specified, you be here, okay? These two electrons that make up the bond in different places, okay? So it's kind of a stretch for our mind to understand that. Another polyatomic ion is carbonate. Carbonate has structure that looks like this. Okay, once you figure it out. There's a formal charge on 2 oxygens, and there's a double bond to the 3rd oxygen. And so again, this, so if we were tasked, okay, write the resonance structures of these, we shouldn't be rotating anything around. We should look at maybe the position of a double bond and a charge, okay? And we should take this structure here and recopy all of the single bonds, okay? Recopy all the single bonds. And then position that double bond in a different location, okay? And that charge in a new location, okay? And then we want to keep the same number of dots on everything. You'll see that there's 6 dots on the singly bonded oxygens. So we put 6 dots on those, right? And you can see how the doubly bonded oxygen up here has only 2 pairs, or 4 total dots. So that would be a good structure. And we can keep going, okay? We could keep going because we can see that, well, what about this oxygen on the left? This oxygen on the left, there is a negative charge. And there's also a double bond here. So we can transpose those locations, okay? Resonance structures differ by the location of a double bond or a triple bond, and usually a charge, like a negative charge or a positive charge. So we could draw this structure here. Again, the steps are to draw out just the single bonds, okay? And then in yellow here, we're going to move the negative charge over here and the double bond over here, okay? And we want to complete the Lewis structure here by adding in all the missing dots here that aren't drawn. There's going to be 6 dots on this oxygen, 6 dots on this singly bonded oxygen, only 4 dots on this doubly bonded oxygen. And don't forget that negative charge on this top oxygen that we did not move. So this is the carbonate ion, okay? You don't want to draw a structure that looks like this, okay? You might Google and find something like this, but this oxygen is pointing in this direction. We have, for the starting material, we don't have an oxygen pointing in the upper left-hand corner, okay? So it looks like you're trying to make a resonance structure by rotating the molecule. Please do not rotate. I can't rotate a spoon and make it change to a fork, all right? But a fork and a spoon are completely different structures, so draw it out, okay? That's in a nutshell how you draw resonance structures. Usually it's for charged things, okay? I'm not going to ask you which resonance structure is better or predict the molecular structure from the resonance structure. But one of your homework problems, this is in the book. There's no real page numbers on the book. It's in section 7.4, resonance. You have this molecule here. This is thiocyanate. Oh wait, I don't want to do this one. I want to do this one. Thiocyanate. Okay. So your job will be to draw a Lewis structure of that and then draw one additional Lewis structure, okay? And again, it's going to differ by a charge and the double bonds, okay? So you expect to have a multiple bond in here. Maybe it's double, maybe it's triple. Expect to have, of course, a negative. And you can move it around a little bit to draw other possibilities, okay? NO2 minus is another one. NO2 minus is called nitrite. Okay, sodium nitrite is a preservative, kind of a meat reddener that's added to luncheon meats, pepperoni, stuff like that. So these will be for your homework, okay? So they are in the book, and I'm telling you that now, so you'll benefit from watching these lectures, or at least the 10 or 5 of you that do watch lectures, okay? So we're done with resonance. Let's talk about the strengths of covalent bonds, okay? We're going to talk about the strengths of covalent bonds, and I just want to mention that in section 7.5, we are going to be skipping lattice energy. Okay, so if you're reading the book, you can skip this section here. And therefore, we are also going to be skipping the Born-Haber cycle, okay? What I want to talk about is the strengths of covalent bonds. Okay, these refer to ionic bonding, and I'm not too interested in that, being an organic chemist by trade. So the idea here is that different atoms bond, okay? They have different bond strengths, okay? Conceptually, we should know that shorter, smaller atoms generally form stronger bonds. Okay. An example of that would be fluorine. Okay. Versus, let's do iodine. Now we know from the periodic table that iodine is a larger atom. And fluorine is a smaller atom. Okay? And if you look at these on table 7.2, I do hope this is in here. I normally don't use this. Okay, so iodine is 150. The units are kilojoules per mole. Okay, and that's the amount of energy you would have to break 1 mole of iodine. Fluorine, it's, oh gosh, is it alphabetical? How is this thing even arranged? It's really random. Okay, so fluorine is 160 kilojoules per mole. Okay, so fluorine is a stronger bond. It requires more energy to break that. Okay, so that's point number 1. Point number 2 is that all else being equal, triple bonds are stronger than double bonds. Than single bonds. Now it's kind of hard to find an element that forms all of these types, but let's just use acetylene, ethylene, and ethane. So here are the Lewis structures of these organic molecules comprised of hydrogen and carbon. And using table 7.2, we can see that a carbon-carbon triple bond is, so that's that central one in all of these molecules, 837 kilojoules per mole. And let me hunt around 611 kilojoules per mole. And the CC is 345, okay? All right, so if you have a friend falling off a cliff, you could hold on to them with one hand. That's a certain amount of energy, saving their lives. If you hold on to them with 2 hands, that's more energy. And I'm sorry, I don't have an analogy for a human with 3 hands, okay? So that's the basics of that. So shorter bonds are stronger bonds, and we're going to use these now to figure out the heats of reaction, right? So let's talk about the heat of reaction. All right. So we have this thing called delta H, or delta H reaction. I like to put a little thing there so you know what it's talking about. And the formula that you want to use here is equal to the sum of the enthalpies of bonds broken minus the enthalpies of bonds formed. And I don't know why, but I'm just going to use the book here since we're doing this in the book. So bonds broken minus bonds formed. I normally use the letter H, but your book uses letter D, and I don't want to have a bunch of questions about that. D represents the bond energy. Bond, and I'm going to put a little note for myself so I don't go crazy. Dissociation energy. Okay, so that's where D comes from. It comes from dissociation, but it's basically the bond energy. All right. Now, as a general comment here, if you have a reaction like this, okay, bonds are going to be broken in the starting materials. Bonds are going to be formed over here in the products. So some students, they like to trivialize things, and they ask me, so it's backwards, right? And I say, well, I'm sorry, forget about that. I was thinking about something else. So The bonds that are going to be broken are here, and the bonds that are formed are here. Pretend like you're making a new Lego creation, and you got to break apart your other ones first to make a new thing. So you're going to break apart your old Lego cars and trucks and stuff like that to make two new Lego trains or planes or whatever, okay? So those of you who played with Legos in your youth know what I'm talking about. So let's do some examples here to, kind of start out slow. So what you need to do is draw the Lewis structure of all reactants products. Okay. You want to use table 2 to get the D's, or the bond association energies. Okay. And then you want to use the formula, right? It's going to be broken minus formed. Okay. When you break bonds, it's endothermic, it takes energy. When you form bonds, it's exothermic. It forms energy or releases energy. I should probably say releases energy. That's a better term. So that's why there's that negative sign there. The negative sign takes care of the release part, okay? So let's do this for ammonia. Hydrogen and nitrogen combine to form ammonia. Now I need to balance this chemical equation, so I'll put a 2 there and a 3 here, okay? Step 1, draw Lewis structures. Hydrogen looks like that. Hydrogen looks like that. Hydrogen looks like that. Why am I drawing 3? Because there's a 3 there. I want to draw 3 of the little pictures. I need 3 of those Lego pieces. What does nitrogen look like? I just need 1 of those. Nitrogen, we've drawn this before in the class, is a triple bond. And ammonia we've drawn looks like, well, there's 2 of them. Ammonia is a central nitrogen, 3 hydrogens, a central nitrogen, 3 hydrogens. Okay. Now, when you use Table 7.2 to get energies, you're just getting the energy of one single type of bond. So an HH bond is worth 436 kilojoules per mole. A nitrogen triple nitrogen is worth 946 kilojoules per mole. And the NH bond is 390. I should mention that in the book you see HN, that's the same as that's the same as NH. Okay, so same thing. You're just looking for HN or NH. All right. Now this is where you ignore the coefficients, like these circled 3 and 2 in this balanced chemical equation. This is where you need to count bonds. So in step 3, we need to count bonds. All right. So the delta H for this reaction is the bonds broken. You see, we have 3 of these bonds. So we have 3 times 436. Okay. We have 1 of those bonds. 946. Okay. And then how many bonds do we have on this side? How many NH bonds do we have? I count 6. I count 6 of them. Okay. So we have 6 of those types of bonds, and they're each worth 390. Okay. And this is where we want to subtract. Okay. Subtract that. So let me grab my calculator and get a final answer here on the screen so we can, admire a number, I guess. So you can use parentheses if you like. I would recommend doing that. 436, 946. Okay, and then minus parentheses 6 times 390, parenthesis, and I get minus 86. Okay. So without having to do any thermochemistry experiments or measuring temperature and all of that, theoretically we could just do the math and calculate it. All right. So that's how you calculate delta H for this chemical reaction. We would say this is exothermic, and overall it releases heat. Let's do another one. Let's do the combustion of methane. This is not balanced, so let me balance it quickly so we have something to work off of. 1 C, 4 H's, 4 O's, 2 and 2, 4 O's. Okay, so here we go. We have a starting point, and the question is, what is delta H? Okay. So step one, we need to draw some Lewis structures. Okay, I'm not going to spend the time to do dot-to-dot structures. I'm just going to draw them all out. Okay. Now, when you draw your Lewis structures, if you have a coefficient of 2, that means 2 molecules. That means 2 pictures. Okay. And so we have to draw those in there. And we have 2 water molecules, don't we? 2 water molecules means 2 of those pictures. Okay. All right, so we've got 1 CH4, 2 oxygens, 1 carbon dioxide, and 2 waters. So that right there is correctly set up. Now we use table 7.2 to find the bond strengths. So a CH is 415. And oxygen, be very careful. Use the double bond, okay? Not the OO, but the O-double-O. That's 498. Okay. And the CO₂, we have 741. Okay. I should mention that this one molecule actually has 2 of those, right? But each one is 741. And then we have an OH bond. We have a bunch of those in this molecule. Let me see if I can find that. Okay, 464. And now we use the formula, right? Delta H is equal to the sum of the bonds broken minus formed. So it's going to be, how many of these bonds do we have? I count 4. Okay, so those are broken. How many oxygen double bonds? I see 2. And then we want to subtract all of the formed ones. Okay, so here's the broken one. We want to subtract all of the molecules that are formed, and we have a bunch of things here, right? So for the carbon dioxide molecule, we have 2 OC double bonds. So 2 times 741. Notice how they're inside of the brackets here. Okay, we also want to subtract the water, right? These bonds are forming as well. How many of these bonds do I break? I'm breaking 4 of those, right? So we're doing this pictorially. We're not using the coefficients anymore at this step. Make sure that all of this is subtracted. So on my calculator, what I like to do is I like to do the bracket stuff first. Okay, so I'm going to calculate all the broken stuff. And use your parentheses on your calculator to keep things straight. Okay. And I'm going to calculate all that in the parentheses. And again, use your parentheses there. And so we'll go ahead and, subtract these 2 numbers. And I get negative 682. Okay. So That's the delta H for this chemical reaction just from the bonds, okay? Now we don't know what the states are, liquid, gas, solid, whatever. We're just counting bonds, okay? So it's a very crude way of just figuring out, based on bonds, which way is more favored or not. We don't know if we're talking about liquids, solids, or gases, so really we can't correlate this with the heats of combustion straight off the bat or something like that, okay? So it's a different way of calculating the delta H, all right? Let's do one more. Sorry, it takes me a while to draw these molecules out carefully. In chemistry, we call this an addition reaction. And ethylene reacts with chlorine to give you dichloroethane. And yeah, there's a bunch of stuff going on here. So in this molecule here, we have two types of bonds. We have a CH bond, which is worth 415. And we have a C double bond, C, which we've previously talked about, is 611. Here we have a chlorine-chlorine bond, which has an energy of 243, okay? And a CH bond over here. All of these bond energies are a positive amount because it takes that amount of energy to break it. We know we're forming it on the right side though. And this is 345. And a CCl is the third type. 330 looks like, okay? All right, so we want to calculate the delta H from that famous formula. It's all of the bonds broken minus the bonds formed. And you'll see that in this balanced chemical equation, we just have 1, 1, 1. That's not going to help us out at all here. We need to count bonds. So there's 4 CH bonds. There's 1 carbon-carbon double bond. Okay, that's the ones we're breaking. I'm presenting this a little bit more slower in this one in case people are still lost. And then we want to subtract all the bonds that are formed. If we count the CHs, we have 4 of those CHs. And we have, let's see, 1 CC. Okay. And we have 2 CCLs. Okay. We have two of those bonds. All right. Now you'll see that actually, technically, nothing happens with the CH. All right. 4 of those CH bonds break, and then you're making your Lego pieces, and you're like, oh, I just have to put those studs right back on their position where I just took them off. So we can, you know, not use that part if you like. If you're more of an advanced student and you see that right off the bat, cool. So we'll use just the bonds that are technically breaking and forming here. So the CC is 611. Okay, that'll be easy to do. That's just one of those and nothing else. Now for the bonds being formed, we have a carbon-carbon single bond, which is 345, and 2 carbon-chlorine bonds, which are 2 times 330. Okay. Now I like to do all the stuff in the bracket first because keep things separated here. So that's 1005, and that's 611. Now we subtract these two. We get a number. And so this is negative 394. So this is another exothermic reaction. All right. So yeah, that's how you calculate delta H from Lewis structures and that sort of thing. Okay. The next section talks about VSEPR. VSEPR is a very big topic. It stands for valence shell pair electron repulsion. Valence shell electron pair, it's actually, VSEPR. So it's like a kind of almost like Viper or something. It has a weird pronunciation. So this is valence shell electron pair repulsion theory, and it's just one theory, and it basically states that electrons repel. Okay. They like to be far apart as possible. And that's why molecules have different shapes or geometries. And we're talking about a 3D shape or a three-dimensional geometry. Okay? So the easiest thing is that there's a lot of observations here that have been made. X-ray crystallography, microwave radiation spectroscopy, and other tools to figure out what the shape of molecules are. Okay? And BeF₂ is found to be linear. Okay? And the idea is that this fluorine has a whole bunch of electrons, this fluorine has a whole bunch of electrons. Technically, it's these electrons that make up the bond and these electrons that make up a bond that want to position themselves as far away as possible on opposite sides of the beryllium atom, giving you an angle of 180 degrees. Okay, so that in a nutshell is valence shell electron pair repulsion theory. Okay, now if you have your central atom, okay, the central atom is called E in this book. Everybody uses a different okay, so these are some definitions. Okay, it's in the book as well if you read through it all. But the central atom is called E. And then bonded atoms are X. Okay. And unshared electron pairs are just called dots in your book, I guess. Dots. I call them U. Your book is not the best here, but so this right here has the general form EX₂. Okay, where you have a central atom bonded to two atoms. All right. Another example would be carbon dioxide. Carbon dioxide we're familiar with is CO₂. We've already drawn the Lewis structure of this many times. This is the E, all right? Each of your oxygen atoms are X, all right? And there's no lone pairs on the central carbon. This also has the general formula EX₂, or a central atom E bonded to two atoms X. Now, it is technically bonded by a double bond, but it doesn't matter, okay? X is a group or atom. All right, it's just an atom. And so another example would be acetylene. All right, let's focus in on this one right here, okay? This is your central atom E. It's bonded to X, which is just, I don't know, a side group, right? And then also this E is bonded to, yeah, it's triply bonded, but don't worry about that. It's bonded to this whole thing, which is just X, all right? So this also is called a linear molecule. The bond angle between this bond and, you know, this bond on the right would be 180 degrees or linear, okay? So again, that's just the very basics of this, okay? Okay, so for figure 7.16, it's summarizing the different spatial arrangements you can have for a central atom surrounded by bonded groups. And this table is with 0 lone pairs on the central atom. So another thing you'll notice is that they're being very lazy with the Lewis structures. They're not drawing any lone pairs on any of the surrounding atoms because that does not influence the geometry of the central atom. So an example of just a linear molecule would be this guy here, and I just want to, let me just highlight it. We call this linear. That means in a line. And we have a central atom that's bonded to 3 groups. So for example, BH3 is boron bonded to 3 groups. And it looks like this. There's a 120 degrees angle between all of the 2 hydrogens, and that's the furthest away you can possibly get 3 groups. But it is in a plane. It's still planar. Now, you get to a complicated molecule here where you have 4 regions of electron density around a central atom. And here we have just 4 hydrogens here surrounding the carbon. And we call this tetrahedral. Okay, tetrahedral. If you look up tetrahedron, it's one of the 4 platonics. It's one of the platonic solids. Okay, and so it has an interesting geometry. If you have a wedge, that means it's coming towards you. Like 3D, put on your 3D goggles and pretend like that's coming towards you. And a dash. So a wedge looks like this. And a dash looks like this. So a dash means it's going behind. Here's methane. The carbon is black and the hydrogens are white. It's a CH4 molecule, and it's not in a plane. Now the angle between these any 3 atoms is 109.5 degrees, okay? And let's talk about the wedges and dashes here. So if I position it so that this hydrogen and this carbon and this hydrogen are in the plane, you will see that this hydrogen here comes out towards us. That would be represented as a wedge. And this hydrogen going away behind us is represented as a dash. Okay? So that's what we are trying to illustrate here by drawing a 3-dimensional space. Okay? The wedge hydrogen means it's coming towards you, and the dash hydrogen away. And things get more complicated when you get to higher amounts of electron density. PF5, for example, is something called trigonal bipyramid. Okay, and you have several different bond angles. You have 120 degrees between the 3 fluorines here that form up the triangle part. So that's the trigonal part of the molecule, and it's a bipyramid because you have a face coming up to the top, and you have a face coming down to the bottom. So it looks like that weird 6-sided die from Dungeons and Dragons. Maybe I shouldn't even draw that, okay? So that's called trigonal bipyramid. And octahedral is when you have 6 things surrounding a central atom. So SF6 is an example of that. We call that octahedral. And they have 2 different bond angles, 90 degrees for the 4 in the kind of the middle, and then 180 degrees from the 2 fluorines on the top and the bottom, or this fluorine and that fluorine, for example. So I don't know why they didn't put 180 in the figure. I think it's a mistake for their book. All right. So that's a little bit about that. All right. Now, once again, we are talking about molecular geometries. Okay. So 2 things, we call it linear. 3 things, we call it trigonal planar. 4 things, we call it tetrahedral. Okay, 5 things, we call it trigonal bipyramid. 6 things, octahedral. Okay, and you do need to memorize these things. There's not a table that gives you all these answers or something, okay? Now, the electron pairs also count as a group that repels another thing. So we want to discuss what do lone pairs do to molecular geometries. So lone pairs are a source of electron density that want to be away from other electrons in a molecule. So we want to look at the molecule NH3, okay? We have electrons that are lone pairs on the nitrogen, and we have electrons that make up the nitrogen-hydrogen bond. And all 4 of these pairs repel one another to position themselves approximately 109.5 degrees away from each other, okay? All angles here are going to be 109.5. That's the angle for a tetrahedron, okay? Now, what does the molecule look like? It looks like this because lone pairs are invisible. They don't show up as a shadow, for example, in X-ray crystallography or other kind of techniques. So the real molecule looks a little bit different, and it looks like a trigonal pyramid, okay, trigonal pyramid. The name is located right here. I hope you can see it on the video, trigonal pyramid, okay? Let me show you what this looks like with these cool little molecular models. This is why I wanted to go into organic chemistry, because you make cool models of things, and I said, wow, I really like playing around with this kind of stuff. I want to, learn more about it. So here's ammonia, okay? Nitrogen actually has 4 things attached to it. It has a lone pair, which is this stick sticking up. It's got 3 hydrogens, okay? So that's ammonia, NH3. But what we want to do is pretend like, those drawings that look like balloons? We want to pretend like we have a needle and pop that, okay? And I'm pretty sure I can't pop this off with one hand. All right, I did it. So now the molecule has this weird shape. It's not planar, okay? It looks like it's planar if I hold it this way, but it's not flat, okay? It's not flat. It's like a trigonal pyramid. So pretend like you're taking a picture of somebody, and this is your tripod, okay? So it forms a triangle, but it has a shape that pokes up into the sky like a pyramid, okay? So that's called trigonal pyramid. So NH3 is a trigonal pyramid, okay? Now, the actual angle here is not 109.5. It's actually about 107 degrees. Now, the reason for that is because lone pairs have a greater repulsion, okay? Lone pairs need more space. All right. Another classic molecule that is usually shown is water. Water is, of course, H2O. It has this Lewis structure. And we normally draw it bent, okay? Bent. It's not linear. Why? Because there are 4 groups attached, okay? There's a lone pair there. There's a lone pair on this oxygen. There's a bonding pair on this oxygen, okay? And there's a bonding pair on this oxygen, okay? And we have 4 things attached. 4 things is called tetrahedral, okay? But grab your needle, pop this balloon, grab a needle, pop this balloon. What is the position of these 2 hydrogen atoms? Well, they're bent, okay? When you look at this molecule, it has the designation bent. If your central atom is E, and your bonded groups are X, and if your pairs are called U, okay, there's one U there, and there's one U there. U stands for unshared electron pairs. This would be EX2U2, okay? So any formula that falls into that category with 2 lone pairs, 2 groups, is going to be bent, okay? It's bent. I didn't say what this one was, But if this is your E, okay, your hydrogen is your X, your surrounded atoms, and if this is an unshared pair, this is EX3U. So that's going to be trigonal pyramid, okay, trigonal pyramid. Okay, the easiest way to think about that is just pop that invisible balloon. Those electrons are, you know, really small, hard to see. You can see a proton from a hydrogen atom. Okay, so that's H2O. All right, that's H2O. In figure 7.19 in your OpenStax chemistry textbook, it gives you now a more complete picture of the molecular geometries. Okay, so here we're talking still about molecular geometry. Okay. Now, we've talked already about what these molecules look like when they have 0 lone pairs. Okay, they have simple names. If you have two things attached, it's called linear, and we called that having a basic designation of EX2. That's not going to show up. EX2. We talked about trigonal planar. All right, trigonal planar, and that's going to be EX3. And we talked about tetrahedral. That's going to be EX4. Okay. We talked about trigonal bipyramid. That's EX5. And this one here with 6 groups is, of course, EX6. But it's called octahedral. I know 8 means oct, but it's because of the faces, and that's off the screen. Okay. Now, we now have begun talking about the influence of lone pairs. When you have lone pairs on the central atom, these electrons twist or bend the shape a little bit more. Okay. If you have something EX2 with an unshared electron pair, so U is that unshared electron pair, it's going to be bent. I like the word bent. It's smaller, shorter, easier to write. It sounds less technical. If you have something like this, like ammonia we talked about, that's going to have something that's going to have the geometry trigonal pyramid. And we talked about water. Okay, water has a bent structure as well, and that's EX2U2. So an example of that is water. An example of this is NH3. Okay, and we already did examples on the first column. Now you have crazy things over here, and there's only 1 or 2 molecules with these interesting names. So you have a seesaw-shaped molecule and T-shaped. There's only 1 or 2 molecules that even fall into that. Linear, quite a few of those. And then down here you have a square pyramid, square planar, and some other weird names. Okay, so linear there as well. Okay, so you have different molecular geometries depending on how many lone pairs you can possibly have contorting the molecule. Okay, so basically to figure out what the molecular structure is, you want to write the Lewis structure of the molecular polyatomic ion, and you want to count the number of regions of electron density, such as lone pairs and bonds around the central atom. You know, you have a single, a double, or triple bonds count as 1 region. And then you want to identify the electron pair geometry. All right. And then you want to use the number of lone pairs to determine the molecular structure. Okay. So these right here are called electron pair geometries. Okay, and then these over here are called, well, they're also called molecular geometries if you don't have any lone pairs. I just want to highlight what the book is saying. And then over here, these are all molecular geometries, okay? So that's how you do this, okay? So let's look at using that table. This is example 711. So we want to write the electron pair geometry and the molecular geometry for each of the following. So we have carbon dioxide, okay? So we write out carbon dioxide, okay? And step 2 is to figure out the electron pair geometry. So carbon here is your central atom, okay? And we have one group right here. We are basically looking at the atom. It's bonded to one atom called oxygen. We don't care about how many dots are on that oxygen. Okay, so it's one group. And remember, we call that group X. Over here, we have one group called X. And the central atom is called E. And on the central atom, there is no lone pairs. Now, the reason I'm making a big stink of this is because a lot of students, they count lone pairs way over here. Well, there's all these lone pairs. That's going to make it, you know, this weird shape. No, we count how many lone pairs are on the central atom, okay? So this is EX2. How do you position those two things far apart away from each other? It's going to be linear, okay? So the electron pair geometry is linear. Okay, we're basically looking at this table, and we are looking at, let me use red here. We're basically looking at this, okay? And then there are no lone pairs, so there's the molecular geometry is the electron pair geometry. So that's the electron pair geometry, which is called linear, and that's also the molecular geometry. The next one we have is boron trichloride. So boron is in group 3, so it has 3 dots, right? Chlorine is in group 7, so we have 7 dots. 7 dots over here, and then we connect some lines to make the bonds, and we stop. Boron is a rule breaker. It's bizarre, and so that's the structure, okay? That's the Lewis structure. Now, we want to count different things here and so on. So boron is my central atom. So that's going to be called E, all right? And then each one of these guys here is a group. It doesn't matter that chlorine has all these lone pairs. It's bonded, right? We're just counting lines here. It's bonded to 3 electron groups, and it has no lone pairs, okay? No lone pairs on the central atom. So 3 groups, let me finish the designation here. It's going to be EX3. There's no U. There's no unshared pairs on the boron. So this is 3 groups. That means that it's going to be, we basically go back to here. Let me use red. If it has 3 groups, we call it trigonal planar. And it has no lone pairs, so the molecular geometry is also trigonal planar. Okay? So we would say the electron geometry is equal to the molecular geometry, which is trigonal planar. Okay? Check your learning. So we're supposed to do carbonate now. Now, carbonate, we've drawn this structure before in the earlier part of this lecture, so I'm just going to slap it up here to save some time. We can just look at one resonance structure. So let's just draw this one here, and let's analyze this, okay? So here's the central atom, okay? And it's bonded to 1, 2, 3 groups, okay? And there's no unshared pairs, and we know that this is called trigonal planar, okay? So the electron geometry and the molecular geometry is the same. It's trigonal planar, okay? So that's a little bit about that. And so let's review water. Water is this molecule here, as we very well know, okay? And this oxygen is bonded to one group, one electron pair group there, one unshared electron pair, and another electron share. Okay, so this has 4 electron groups. Okay, remember, a group can be a bond to a hydrogen, or it can be just a lone pair. Sometimes we draw a line to a lone pair. I kind of like how the book does that. So 4 electron groups is going to tell us, because you're counting the electrons, it's called the electronic geometry. Okay, and that's tetrahedral, right? Tetrahedral. If you could view the electrons, it would be a tetrahedral geometry. Now what we do is we take a needle and we pretend like these are balloons, and we pop those two. What is the molecule going to look like? Well, we pretend like the electrons are invisible, and the molecular geometry is going to be called bent. Let's go back to the table and make sure we can see that, okay? So we found 4 things attached. So that was a tetrahedral electronic geometry for the H2O molecule. And we saw that there was, the H2 molecule had 2 lone pairs, so it's bent. Okay, it's bent. All right, so let's do another one. Okay. Now, some of these molecules can be pretty weird looking. There's 2 different possibilities oftentimes for how you can do things. But let's do XeF₂. Okay, XeF₂. So step 1 is to draw the Lewis structure. So we set up our skeleton. Xenon is in group 8, so we need 8 valence electrons to get us started. Fluorine is in group 7, so we need 7 valence electrons to get us started. 7 over here as well. Make a line, which is a bond. Okay, and then count your pairs. There's 1, 2, 3, 4, 5. Okay, so there's 5 total groups. 5 total groups means, let's go back and look at the table if you're confused about the names of the basic groups. 5 total groups is called trigonal bipyramid. Okay, so trigonal bipyramid is when your central atom is bonded to 5 total electron groups. So that's an electron geometry. Of trigonal bipyramid. Okay, and now this is pretty far down in the table. This is my cutoff for where you need to memorize things. Let me make this really maybe bold. Yeah. All right. So let me highlight the section that you should memorize. Okay, you should memorize the basic geometries for 2, 3, 4, 5, and 6 for this column here. And you should memorize bent molecules, trigonal bipyramid, and bent molecules. Okay, and okay, so within the purple mark, learn these. All right. Now, XeF₂, we said, was a molecule that had 2 5 total electron groups. So this is something that we should memorize. We should call it a trigonal bipyramid, okay? But you might not know, well, which one is it, right? Like, so for example, when you have 2 xenon atoms and 3 unshared electron pairs, that turns out to be linear. So the molecular geometry is linear, okay? Okay, and you might have thought maybe it would be bent or something like that, all right? So, which is a hypothesis. Let's do another one, XeF₄. Okay, so XeF₄, step 1, draw the Lewis structure. This is why it's very important to be able to draw Lewis structures. It's the first step in figuring out all the other answers. 8, 7, 7, 7, 7, draw a bond, draw a bond, count groups. So there's 1, 2, 3, 4, 5, 6. So you should know that 6 groups. The electronic geometry of this weird molecule is something we affectionately refer to as octahedral. Okay. You don't need to know this part, but if you go back to that table and you look, it's outside of the purple box, but this actually has a molecular geometry of square planar. Okay, square planar. Now, let's talk about large molecules, okay? So don't freak out on me here. Let's consider large molecules. Okay? And what do we got here? Looks like glycine. So we have a protein. Okay, and this question might be phrased in different ways. What is the molecular geometry? What is the electronic geometry? Or what is the bond angle? Now, this is not a protractor question. So, for example, if I asked, what is this bond angle? Some students would say 90, because it looks like it's 90 degrees. Well, what you need to do is count bonds and then figure out what the electronic geometry is and think back to what we've learned, okay? So, for example, this is what we do. We count groups. Four means tetrahedral. Which means that it has an angle of 109.5 degrees. Okay? Let's do another one. What if we were asked to identify, okay, what is this bond between the oxygen, carbon, oxygen? Okay, what's that bond? Angle, you know, is it 120, 90, 180? What is it supposed to be? What is it? All right, so again, what you do is you look at this as the central atom and you count groups. Now here I'm going to slow down a little bit in case I lost you. When you count groups to this carbon, this is one group. This is one group. Okay, because there's a line going that way. And here's a line. This is one whole big old group. Okay? So we say that that carbon has 3 groups. Okay? 3 groups means, let me think, right? It means you have a trigonal planar geometry. Okay. How about this part of the molecule? I can't really highlight on black. Let's see. I'll highlight with white then. So how about this part of the molecule right here? Okay, the nitrogen. What is the geometry, molecular geometry of that nitrogen? If you look, we have a hydrogen, and then we have a humongous part of the molecule that way in a lone pair. And so if you look at this, this looks just like ammonia. It's trigonal pyramid. Trigonal pyramidal or trigonal pyramid, okay? So it's got 3 groups and 1 lone pair, so that's just like ammonia, okay? How about the oxygen right here? Well, that oxygen looks just like water, so we would say that's bent, okay, bent. And here we're talking about molecular geometries, okay, molecular geometries. All right, so if you see really big molecules, don't freak out. One of the questions I will ask you about is aspirin. Aspirin has this Lewis structure. We always do this one last when people have a headache and they're thinking, wow, I need to get some aspirin. Oops. So you might be asked, what is the geometry about that carbon, about this oxygen, maybe about this carbon, something like that. You might be asked, what is the bond angle here? What is the bond angle here? Okay. What's the bond angle here? Etc. Okay. And when you're asked for bond angles, you give the idealized bond angles. The idealized bond angles are in that table way back in the beginning, okay? So the important thing to think about is the polarity, okay? Polarity is mentioned ever so briefly in this general chemistry textbook, but it's a humongous part of future classes if you go on to take organic chemistry, okay? Polar molecules have unequal distribution of electron density in them, okay? So we talked about fluorine, how it's equal and opposite, right? And how hydrogen chloride, for example, would be unequal bonding. Now it turns out when you have something like that's linear, for example, this oxygen is delta minus, this oxygen is delta minus, and this carbon is delta plus. There is a polar bond in equal and opposite directions. So we say that this molecule is non-polar. All linear molecules are non-polar. Okay? It doesn't matter if you have the carbon dioxide, which falls into the EX2 group, or xenon fluoride, which falls into the, if I remember, EX2U3 grouping. Okay, so all linear molecules are nonpolar. BF3 has 3 polar bonds that point into corners of a triangle, and that's also non-polar. Okay? Methane, well, let's just do chlorine here because chlorine's a electronegative atom. Okay, that was quick, but I counted delta minus on the chlorines, delta plus on the carbons. So you'd have to imagine some astronauts going out into space and playing tug of war in a weird way in three-dimensional space. You have 4 bonds that are all pointing into the corners of a tetrahedron, and that's also non-polar. Okay, so let's go back to our table and just highlight this really quick because I think I might be running out of time. Let's use blue. We haven't used blue before. What are the non-polar molecules? Okay, let's make a note, non-polar. Let's circle that label. This is going to be nonpolar. This is going to be nonpolar. Whenever you have a molecule without lone pairs on the central atom, it's going to be nonpolar. That's an easy way to remember it. However, there are some symmetrical examples that are nonpolar as well, and that's right here, which is linear. That's right here, which is linear. And that's going to be, where's that? Right here, the square planar, which is like 2 linear molecules together, okay? So those are outside the purple, but you can see how, like, if you don't have lone pairs on the central atom, it's going to be symmetrical and it's going to be nonpolar. But there's a caveat for that, and I just want to emphasize that here. It's equal and opposite, okay? If I have a molecule like this with 4 bromines, I need to recognize that all of these bromines are equal in electronegative strength, and it's going to be nonpolar, okay? But a molecule like this, chloroform, is going to be polar, okay? It is going to be polar because hydrogen is not the same as chlorine, okay? So keep that in mind. The outside peripheral atoms have to be all identical for it to fall into that category of a blue circle on that table, okay? So that's it for today for now, and we have a couple more lectures. Well, it's difficult to explain the pace of this chapter, but that's where I want to end today's class.